Now let's see now the third example of subspaces and vector spaces. Well, our starting point this time, let's consider R3, the three-dimensional space. So we have here three vectors, so 1, 0, 1, 0, 0, 1, and 1, 2, 0. Geometrically, we have here the x-axis here, the y-axis here, and the vertical axis is the z-axis. So we have here these three vectors, and I already know if I have the set of these three vectors, the span of it, meaning all the linear combinations of these three, cover the entire three-dimensional space. In other words, every point in three-dimensional space correspond to some a, b, and c numbers that, combining these vectors, gives us that location. Here on the right, we see examples of subspaces. So the pink-blue plane, so we find here, so the pink vector and the blue vector. Imagine a plane that contains these two vectors. So it's the span of the vectors that you find here. All linear combinations of these two. So it's a two-dimensional space that contains the origin. Look at the plane, contains the origin, which corresponds when I multiply this vector and this vector by the zero. Additionally, from these two, because I'm combining these two elements, I can write the generic form of the vectors that start at origin and land in this plane, meaning A to A, B. How do I arrive at this? Remember, I arrived at this by writing A, 1, 2, 0, plus B, 0, 0, 1. So every element living in this plane, the pink-blue plane, every vector on it has this form, but I can write a more compact way of writing this, namely, the vector with three entries, so A, 2A was 0 because B times 0 is 0, and A times 0 is 0 plus B times 1, which is B, which is again what you find here. As a second subspace, we have the xy plane. The xy plane is the plane, it's like the floor of the thing, right? Like the floor. Contains this line and this line and this line and this line. Okay? So it's the span of 1, 0, 0, which is, by the way, a vector that looks like this, and 0, 0, 1, 0, which is somewhat like this. Can you see? So it's a plane that contains these two vectors. And of course, the generic element of it, well, it's just A and B. And of course, the third entry, the z-axis coordinate is 0 all the time, because we live in this plane. But again, this vector space contains the origin, and any linear combination of it always gives me an element in the xy plane, just like it happened in the pink-blue plane. Finally, the yellow line. The yellow line, while these two vector spaces are two-dimensional, this vector space is just one-dimensional. So it's because it only spans the starting value is just one vector. So it's a 1, 0, 1. So it's a line that contains the yellow vector here. Of course, it has a form A, 0A. All of these are examples of subspaces of the entire R3, the three-dimensional space. Because all of them, of these vector spaces that you find here in this list, are subsets of. Now, these examples of vector spaces and vector subspaces shows us something important. Consider the following subspaces of R3, namely the xy plane and the vertical axis. Just focus on those two. Let me write. You have U, which is the xy plane, and V, which is the z-axis. Consider these two subspaces of R3. I claim, and I think it's quite easy for you to see, that any vector R living in R3 can be written as an element of U plus an element of V all the time. For example, if I choose this vector that starts at origin and that ends up here at this point, can be written as this vector, so the U vector, which lives in the xy plane, plus this vector here, which lives in the z-axis. So this is V. So any point that you choose is like a spaceship. You move horizontally and then you shoot up. Any point works. This is a very important observation because the idea is important because it tells us that R cubed, the elements of R cubed, the form of it, are always of the form U plus V, where U belongs to U and V belongs to the vector space V. So I'm specifying now a very concrete form for the elements of R3. Of course, I need to first tell what is U and V, in this case the xy plane and the z-axis, but after I've done that, I can claim, and I can see intuitively, that any vector in R3 has the form of U plus V. There is a special notation for this, by the way. A special notation. And the special notation is U sum, which means the direct sum of V. So R3 is a direct sum of the xy plane and the z-axis, which means I can write any vector in R3 as an element of U plus a vector of V, just like I said here. Notice that R3 can be, you see, R3 is being decomposed into two subspaces, U plus V, the direct sum of spaces. But R3 can also be decomposed in other ways. For example, U could be the subspace, the yellow line subspace. And the V could be the plane which is perpendicular, you can see the plane which is perpendicular to the yellow line, which contains the origin, by the way. I did not draw that, but you can imagine it. If I consider this U and V, I can also write any vector in R3 as a summation of a vector living on the yellow line plus a vector living in the space perpendicular to that line. Again, another direct sum.